Okay, welcome everyone. It's great to see all of you here after our summer break. This is the first talk after the summer break, and we're now going to be going back to our usual 2-week schedule. So there'll be a talk every other week. And today it's our great pleasure to have Marcello Porta giving us a talk about the universality of transport in many-body lattice models. Marcello, take it away.
So thank you very much, Ian, for the introduction, and thanks a lot for the invitation to all the organizers, to Hal, to Margherita, and to Kasia. It's really a great pleasure to be here today and to see all of you again for this start. Okay, so today I would like to review some recent works that where I've been involved about transport for many-body lattice models of relevance for condensed matter physics. And so let me start with an overview of this presentation. So I will start by making an introduction to two very beautiful universal transport phenomena in condensed matter, which involve two different physical samples. One is going to be about the quantum Hall effect, which is a very famous transport phenomenon in condensed matter. And the other one is a bit more recent. It's going to be about graphene. Okay, so these are two different type of materials. Their common point is that they're both 2 dimensions. Okay, so we'll be talking about thin materials. So after this introduction about what do I mean by universal transport, I will spend some time in introducing a general setting of many-body lattice models. So it will be about fermionic models on a lattice. And at this stage, I will not specify any model. In fact, I will just be considering general short-ranged weakly interacting lattice models, and I will introduce a few tools that I will be referring to in the rest of the talk. So quantum dynamics, linear response approximation, and then 2 main objects that will appear until the end of the talk, namely real-time correlation functions, imaginary time correlation functions, and their connection via analytic continuation, or also called Wick rotation. So I will then, so I will try to stress what are the general questions I would like to understand, and then I will focus on a specific model for which I will present the theorem. This is going to be a class of weakly interacting fermionic models relevant for describing quantum Hall systems on a cylinder. Okay, so there will be some boundaries involved, and the question that I will be studying here is going to be about computing the so-called edge response function from a microscopic model. And the approach that I would like to present here is somehow relatively general. It has been used to study different models, in fact, and it's based on 3 main ingredients. The first one is rigorous renormalization group analysis of imaginary time or Euclidean correlation functions. The second one is a precise study of the scaling limit of the correlation function. So the large decay, somehow the contribution to the correlation function that dominates scaling at large distances. In some cases, this is accessible, and it could have some special integrability features, as we will see later. And finally, the last ingredient is to understand how to deal with all the finite scale deviations from the scaling limit, which are in general non-explicit, but which in some cases can be constrained using lattice conservation laws in the form of word identities. This is going to be a crucial ingredient to prove universality later. And at the end, I will conclude. So let me say, I will not really say much about the renormalization group analysis. The technical details of that, I prefer this not become too technical, but I will tell you what one can prove with renormalization, and then I will tell you how, in cases in one can prove universality, how this is done, starting from the input that the renormalization gives. So let me start with this introduction. Let me start with the quantum Hall effect. So this is a transport phenomenon which I'm pretty sure most or maybe all of you are familiar with, but let me anyway review it. So the setting is about very thin materials, so ideally 2-dimensional ones, And the experimental situation is the one you see in this picture. We have a very thin material which is exposed to a transverse magnetic field and to an in-plane electric field along this arrow here. Okay, so if you just accept classical electrodynamics, then what you expect to observe is that there's going to be an accumulation of charges, opposite charges on the two sides of the slab. Okay, and then there's going to be a voltage drop because of this. So this is the setting that was considered by von Klitzing at the beginning of the 80s, and then the remarkable observation is that for special class of materials known as insulators, and at very low temperatures, something remarkable happens. So if you look at the current that develops on the sample at first order in the applied electric field, so if you take a linear response approximation, then the object of interest is the conductivity matrix, which is a 2x2 matrix telling you how the current develops as a function of the electric. And the observation about the quantum Hall effect is summarized here. It's a statement about the conductivity matrix. The diagonal part is 0, and that's in fact because the system is an insulator. But the interesting part about it is that the off-diagonal part is quantized in units of this fundamental constant. Okay, so this is a very remarkably it's a remarkably precise measurements, and here on the right you see measurements for the resistivity matrix, which is the inverse of the conductivity matrix. So, as I said, this is a phenomenon relevant for insulating materials, and one way of realizing an insulator from a mathematical point of view is to look at, let's say, non-interacting Fermi gas with a Hamiltonian H, and to choose the Fermi level of the system to be in a spectral gap of the Hamiltonian. Okay, so this is one way of somehow describing mathematically an insulator. More generally, you could have that the Fermi level lies in what is called the mobility gap, which is the situation if you have strong disorder. Okay, so that's an example of a universal transport phenomenon. This transport coefficient only depends on fundamental constants. And it turns out that similar phenomena also happen in different compounds, which are not insulating materials, in fact. So here I'm mentioning the case of graphene. We're again talking about the two-dimensional system. So it's one layer of graphite. And this system turns out to be not an insulator, but rather a semi-metal. So at charge neutrality, the Fermi surface of the system is given by isolated points, as one can find for a very simple model of graphene. Okay, so the model I'm referring to here is the Laplacian on the honeycomb lattice that only describes hopping of fermions from one side to its nearest neighbors. If you diagonalize this Schrödinger operator in momentum space, you can find out the energy bands of this Hamiltonian, and what you find out are these two energy bands that touch at a number of inequivalent points. Okay, so only two of these points are independent because of periodicity on the Brillouin zone, and close to these points you see this peculiar relativistic, or if you want, linear behavior of energy as a function of momentum. Okay, so that's another type of two-dimensional system, and the remarkable observation here is about the longitudinal conductivity instead. So just in a picture, look at this smaller picture here. These are experimental measurements for the longitudinal conductivity in units of this fundamental constant. And this one here has to be read in the sense that the sigma 1,1 is actually equal to this quantity up to, well, small fluctuations around. Okay, again, we have a transport phenomenon which seems to only depend on fundamental constant. This time the quantization is not an integer, but it's pi over 2. Okay, so this is about graphene, and again, this is not an insulating material. It has conical intersections, and in fact, this transport phenomenon turns out to be relevant more generally for quantum Hall transitions, where gap closure happens with conical intersections. Okay, so these are two very striking observations, and it turns out that in fact there are rigorous results that allow to understand that. And so for the quantum Hall effect, that's a long story. In fact, thanks to the work of many theoretical and mathematical physicists, by now we have a very good mathematical understanding of the quantum Hall effect in terms of topological argument or index theory argument. So these works I'm mentioning here refer to non-interacting systems, but in the last years there has been progress also for many body systems with a spectral gap, and that's this work of Hastings and Michalakis. There is a dual, I mean, there is somehow a complementary, if you want, a different point of view on this phenomenon, which has been pioneered by Jürg Fröhlich, beginning of the 90s, which is a point of view from the point which relies on an effective field theory approach. Somehow the idea is to classify effective actions for non-relativistic Fermi gases. And these are effective actions parameterized by external gauge fields that introduce the electromagnetic field in the system. And the quantization of the whole conductivity can actually be understood in terms of properties of these effective actions. So this was based, in fact, on fundamental principles on gauge invariance and anomaly cancellations, and I will say something about it later. And that has been, in fact, also a big inspiration for what we did afterwards. Okay, so what I would like to discuss today is about transport for many-body lattice models, and I would like to discuss methods that have been used for gapped and gapless systems. And somehow the main objective here is to understand universality starting from many-body lattice models and relying on lattice and emergent gauge symmetry. So this is going to be the main tool we will use, in fact, the main input we will use to prove these quantization results. So here I'm mentioning works which are relevant to what I briefly introduced now. So with Giuliano and Mastropietro, we in fact proved the universality of graphene's conductivity for short-range interactions. And then again, with Giuliano and Mastropietro, we also obtained a proof of quantization of the many-body Hall conductivity by actually showing that it's universal. So in particular, interaction independent. And this has also been extended in collaboration with Ian Joustlin to the case of studying phase transition or topological phase transition between different Hall phases in a specific model. Okay, so what I would like to do next is to describe this the general setting I will be working on, and then later I will discuss the application to edge transport for interacting Hall system, which is again a case in which the low energy excitations are gapless and described effectively by one-dimensional relativistic fermions. All right, so let me introduce the setting. So I will consider fermions on a d-dimensional lattice lambda L. So L will always denote the side of this lattice. So you could, I mean, an example would be lattice with periodic boundary condition, but later I will actually consider also different shapes. And the typical Hamiltonian I will consider as a very standard one. There is a first term that is a second quantization of a single particle Hamiltonian H, and the second term is a second quantization of a density-density interaction described by this potential V. Okay, so A and the star are the usual fermionic creation and annihilation operators. So what I will assume for the moment is only that these operators H and V are finite ranged, and then later I will actually specify on a concrete model. So this is a Hamiltonian generates an evolution which you can see as an evolution for observables via this Heisenberg dynamics, as we all know. And also, once you have a Hamiltonian, you can introduce an equilibrium state, which is the usual grand canonical Gibbs state. Okay, so this is parameterized by inverse temperature and by the chemical potential, and it defines expectation values of observables in this. So another object I'm introducing here is the so-called Euclidean or imaginary time evolution of observables, which is defined here. It looks very much like this operator when t is replaced by minus it, and when the Hamiltonian is shifted by minus mu times the number operator. So of course this makes no difference if O commutes with the number operator, but if not, this in general is a different object. And so this is the imaginary time evolution of O, and the reason why I'm introducing it is that there is this very nice, very important identity, in fact, which will play a role in the following. That's called the Kubo-Martin-Schwinger or KMS identity. Okay, so at the present stage, this is really just a consequence of cyclicity of the trace, but as you will see, as I will comment on, it has far-reaching implications for transport. Okay, so until now everything was at equilibrium, so the dynamics of the state was trivial, in fact. And so if you want to observe a non-trivial transport on the system, one way of somehow introducing a flow of let's say of charge is to make the Hamiltonian time dependent. Okay, so that's what we're doing here. We make the Hamiltonian time dependent thanks to this perturbation here, which is going to be small because of this parameter epsilon, and it's going to be slow in time because of this adiabatic factor e to the n. Okay, so P is going to be an extensive perturbation. You can think of it as a sum of densities multiplied by potential, and so later I'll make a specific choice. And my convention is that eta is a positive number and t is less or equal than 0. Okay, so the evolution starts, if you want, at equilibrium at time t equal to -infinity with the equilibrium state, and then I generate a non-trivial evolution of the state by solving the Schrödinger von Neumann equation for the state. Okay. So that is the setting, and then the question that I would like to discuss is about variation of physical quantities. Okay, so this is the variation of the observable at time t equal to 0 minus the observable at equilibrium divided by epsilon, which is the strength of the perturbation. Okay, so that's the response of the observable with respect to because of the presence of this time-dependent perturbation, and this you can. I mean, one thing you can do is to try to analyze this by expanding in the parameter epsilon. Okay, so if you do that, you get a first-order term, which is explicit, and that's the so-called linear response of the observable, and then there will be higher-order terms that involve the higher powers in epsilon. Okay, so this is done by Duhamel expansion, and the first-order term is what is given by this formula here. That's also called the Kubo formula. So this is the setting, and it turns out that many interesting transport phenomena, such as the integer quantum Hall effect and the conductivity of graphene, these are captured by already the linear response transport coefficient. Okay, so just by the linear response is able somehow to reproduce what is observed in what I showed you before. And there are, at this stage, two difficult and complementary problems that one would like to study mathematically. The first one is to be able to compute the linear response rigorously in the limit in which the system gets infinitely large and the adiabatic parameter goes to 0, and also maybe in the limit in which the temperature goes to 0. And another problem is to understand the validity, the rigorous validity of the linear response ansatz by showing that this error term is actually subleading in epsilon, uniform in the size of the system and in the adiabatic parameter. Okay, so these are two hard problems in this many-body setting, and at this stage, since we didn't really specify a model, they're essentially intractable. Okay, so this is way too hard for this level of generality. So concerning this problem too, it turns out that this has been solved for gapped many-body systems, so many-body Hamiltonians with a spectral gap at the Fermi level. And this is, in fact, a consequence of the many-body adiabatic theorem that was proved by Bachmann, de Roek, and Frass, a few years ago. So this holds at 0 temperature and for arbitrarily large samples. And a key assumption here is that the spectral gap of the Hamiltonian remains open for all times. Okay, so this H of t has a spectral gap for all time. So the other result I'm mentioning is this work of Stefan Teufel, which is about somehow extension of this approach to the setting in which the spectral gap might be closed in time by the perturbation. So this also allows for a suitable class of large perturbations, and the linear response holds as a somehow corollary of the construction of this non-equilibrium almost steady states. And finally, the last result I'm mentioning here is a work where I've been involved with collaboration with Raphael Greenblatt, Marcus Lange, and Giovanna Marcelli. So what we did here was to somehow we use a different set of tools, and in fact what we obtained is to prove that the expectation values of local observables can be written in terms of a convergent expansion in imaginary times. Okay, so this is something that for which there are much better estimates than in real time, and this connection between real and imaginary times is in fact rigorously proved using a version of the Wick rotation at every order in this Duhamel expansion. So the bonus of that is that it holds also at positive temperature, small positive temperature uniformly in the size of the system, but which have to shrink when the adiabatic parameter goes to 0. Okay, so what I would like to do today is to focus on point one. So I would like to focus on, in fact, computing this. So starting from the linear response ansatz for gapless systems and make rigorous statements about it. And this is, in fact, a non-trivial problem even for non-interacting models. It strongly depends on the spectral properties of the Hamiltonian at the Fermi level. So I was initially planning of also telling you something about validity of linear response, but I realized that time would not have been enough. I have some backup slides in case, of course, someone is interested, but I will not say much about it, unfortunately. Okay, so let me start from, again, Kubo formula for linear response, and let me point out some obvious difficulties that one has to face in studying this object. So one obvious difficulty that one has to deal with is that here you have a time integral which involves, unbounded interval of time, which I mean, you have to control in the limit in which eta goes to 0. Okay, so of course this exponential factor is useful, but it's not useful if then ultimately eta goes to 0, and it's extremely hard to extract decay from this type of correlation function for general non-integrable many-body systems. So one way of studying this problem is by complex deformation, and that's something that I personally find very nice, and it goes as follows. So let me introduce an approximation of this adiabatic parameter eta to be called eta beta. This is a point on a lattice with a very small mesh of order 1 over beta. Okay, so let me call eta beta to be the best approximation on this lattice of the adiabatic parameter eta. Okay, so then the claim, and that's in fact not difficult to prove, is that if you look at this Kubo formula replacing the adiabatic parameter by this eta beta, then this is exactly equal to the Fourier transform of a Euclidean correlation function. Okay, so this exponential factor becomes a phase factor, and this real-time correlation function is replaced by an imaginary time order imaginary time correlation function. So this is, of course, special for these values of eta, and then you have to ask yourself what happens if, well, to the difference between these two guys, and then it turns out that the difference of these two integrals can be actually proved to be small uniformly in the system size, and as beta goes to infinity as a consequence of Lieb-Robinson bounds. Okay. So Lieb-Robinson bounds allows you to bound this commutator in a way that spares you the volume growth of the system, and then this eta is because that's you have to control the time integral with this exponential. Okay, so this is nice. It tells you that when beta goes to infinity, in fact, this Kubo formula can be studied in imaginary times, and that's it's a good starting point because it turns out that there is a very good direct control on this type of correlation function in certain cases. So in particular, if you choose your Fermi level to be away from the spectrum of the non-interacting Hamiltonian, and if the coupling strength is small enough, then it's possible to prove that this Euclidean correlation function decay exponentially fast. Okay, so this is an exponential decay in space and in time with respect to this periodic distance on the circle. Okay, so this is now something that allows in particular to prove that this object is finite, and actually if you have good control on this correlation, you can even try to write down series expansion for this object as power of lambda. So that's useful information, and in fact it can be extended to higher commutators appearing in the Duhamel expansion, and in fact all of them can be rotated to Fourier transforms of Euclidean correlation functions, and that's in fact the way that we use to prove validity of linear response for gap systems in this reason. All right, so what about, I mean, how is this decay proved? Well, this is proved via cluster expansion. So we start from the fact that the Gibbs state of the non-interacting Hamiltonian with a spectral gap has nice decay properties, and then it turns out that these properties for small lambda transfer also to the interacting Gibbs state by expanding in lambda. Okay, so the crucial tool that makes perturbation theory well behaved and in fact convergent is a beautiful identity for fermionic cumulants that goes under the name of Bridges-Battle-Federbush formula that allows to prove the convergence of the cluster expansion for fermions. So this is nice, and it's in fact useful for gap systems, so for describing insulators. But as it is, you cannot directly apply it to studying gapless models because of infrared divergences. So this perturbation theory, if the single particle Hamiltonian does not have a spectral gap, is very badly behaved when temperature goes to 0 and volume goes to 0. So to deal with this problem, you have to use, one way to deal with this problem is to use rigorous renormalization group methods that have been developed starting from the mid-80s by many people, and in fact, starting from the 90s, they have been used also to study condensed matter systems in the absence of a spectral gap. So in the last years, this renormalization group approach has been used to study transport, in fact, at 0 temperature. And here I mention 3 different settings in which this has been done. So it has been done for one-dimensional systems. So let's say the Laplacian in 1D with a short-range many-body interaction. So one-dimensional metals. And this is thanks to the work of Benfatto, Falco, Mastropietro. So they've been able to use the normalization group to compute response functions, and the main somehow one important observation about this class of models is that their scaling limit is somehow well described by the integrable field theory, which is called the Lattinger liquid. Okay, so this emergent integrability structure at large distances plays an important role in this analysis. The other cases, and that's where I was also involved, is about 2D and 3D semimetals, so materials with point-like Fermi surface. So before we've seen graphene, but in 3 dimensions there are also these Vi semimetals, which also have point-like Fermi surface. In both cases, the low energy excitation of the system are described by emergent relativistic particles, so 2 + 1 dimensional or 3 + 1 dimensional massless Dirac fermions. So in all these cases, there are interesting transport properties that can be accessed via RG. And what I would like to discuss in a bit is the application of these tools to study edge transport for 2-dimensional quantum Hall systems, which is somehow sits in between these 2 cases, because somehow from the edge perspective, we will be talking about 1-dimensional systems, but the original model is actually a 2-dimensional. So, okay, so before doing that, let me tell you what is the typical outcome of the renormalization group analysis for studying transport coefficient, so in particular for studying correlation function. So the typical outcome of the renormalization group analysis is a statement, is a precise decay estimate for the Euclidean correlation function of the many-body system. Okay, so here I'm looking at the connected correlation function in imaginary time for observables which are local and supported in 2 subsets of the lattice X and Y. And so whenever RG works and whenever you can use it to study infinite volume and 0 temperature, what it gives you is a very good understanding of the decay properties of this correlation function as I'm writing here. So there is a first term that captures the scaling limit of the correlation function and in fact the large scale behavior of this object. And then there is another term that takes into account deviation from the scaling limit, which in fact decays faster in space and in imaginary time. Okay, so just as an example, if you consider weakly interacting graphene, and if you take these 2 observables to be density insertions, then it turns out that this first term decays as it would for 2 + 1 dimensional massless Dirac fermions. So it would decay as 1 over space-time distance to the power 4. And the other term instead is much less explicit, but you know it decays faster. So the scaling exponent here is not 2, but it's 2 + theta, where theta is some positive number. So this is, of course, nice for looking at correlation functions, but not so useful for computing transport coefficients because of this obvious fact that if you replace this decomposition inside the Wick-rotated linear response, which is in fact a Fourier transform of the correlation function, then what you end up with is a sum of 2 terms. The first one, which involves the Fourier transform of the scaling limit, and the second one that involves the Fourier transform of the regular part. But this is not smaller than the first. I mean, this term is not smaller than Fermi, it's just more regular in this parameter eta. Okay, so if your goal is to compute this object in some limit, then somehow this type of analysis is not enough. I mean, you might have that the scaling limit has some nice integrability feature, there are some nice exact formulas for that, but the regular part in general does not have all these features, and it's in fact not smaller than the first one, it's just more regular in the parameter eta. Okay, so one thing you have to figure out is how to access this very non-explicit part exploiting general information about the system. In particular, one information that is very useful to keep in mind is the fact that the two-dimensional model has to satisfy some conservation laws, and you will see later how I will use that. Okay, so this is very general. Now I would like to move to a specific case in which these somehow this approach, these ideas can be applied. And that's a setting of two-dimensional quantum systems relevant for the quantum Hall effect. So a hallmark, in fact, of topological transport is what is called the BuEdge duality, which is the observation that if you have a two-dimensional quantum Hall system, and if you are able to measure a non-zero Hall conductivity in the bulk of the sample, then this necessarily has to come with stable edge currents flowing on the boundaries. Okay, so this was an observation that was, in fact, pioneered by Halperin at the beginning of the 80s, and it is by now a very important feature of all the topological phases of matter that have been discussed, that have been discovered afterwards. So let me have a closer look at this phenomenon from a microscopic point of view. So let me denote by H the lattice Hamiltonian for a quantum Hall system on the half space. Okay, so now the model comes with, it's defined on an infinite lattice, but it comes with an infinite boundary because of the fact that here the lattice terminates. So it's Z times N. Okay, so let me also suppose that the Hamiltonian is translation invariant in the direction of the edge. Okay, so if so, you can actually partially diagonalize the problem in momentum space by essentially the Fourier transform. So you can introduce this H hat K, which is a effective one-dimensional Hamiltonian, which is obtained by taking the partial Fourier transform of H in the direction of the edge, which is the translation invariant direction. And then you might want to look at the spectrum of this H hat K, and this is what I'm doing here. So this picture here plots the spectrum of H hat K as a function of K for K on the circle. And what you could have is that the spectrum is given by, for a given K, by some gray bands, which would agree with the spectrum of the system without the boundary. So it's somehow the bulk spectrum. But then on top of it, you might have eigenvalues that correspond, let's say, to points on this red curve. And as a function of K, they draw curves that emerge from the lower band and dive into the upper band by closing the spectral gap. Okay, so these are, for a given value of K, they correspond to so-called edge modes. And in fact, these are generalized eigenstates of the Hamiltonian H, which behave as a plane wave on the boundary. So they are responsible for metallic transport on the boundary, but they decay exponentially fast in the bulk. So they are almost one-dimensional states that live on the boundary of the system. Right, so this is what could happen. In fact, it turns out that there is a deep duality between the value of the Hall conductivity for a system with no boundaries and the emergence of edge modes for a system with, let's say, one boundary like here. This is the content of this identity, which is the core of the BuEdge duality. Okay, so on the left-hand side, you have the Hall conductivity for the system without boundaries and with a bulk spectral gap. On the right-hand side, you have the sum of the chiralities of the edge modes. So that's a sum of plus or minus 1 that just tells you what are the directional propagations of the edge modes on a given edge. So how is this defined? Well, V of omega is just the velocity of the edge mode defined as the derivative of this dispersion as a function of K at the Fermi level. And then this derivative as a sign, of course, and this sign tells you about the direction of propagation of the edge mode. So that is something that is by now rigorously understood for for non-interacting models, starting from the work of Hatsuga in the 90s, and then this has been, in fact, extended to a larger class of models, also disordered systems by different groups. And also, it has a very beautiful explanation in terms of effective quantum field theory. In fact, again, in terms of scaling limit of effective actions for non-relativistic QFTs, and that was a point of view, powerful point of view that was pioneered by Froelich and Venn and others. But the question that somehow I would like to discuss is how to access edge transform from a many-body microscopic model. So I would like to define an edge response function starting from a many-body microscopic model and try to make a rigorous statement about it. Okay, so let me introduce the setting. So the setting about interacting lattice fermions on a cylinder now. So this lambda L is going to be a lattice with side L, but I will assume that I have something like that. So Dirichlet boundary condition on the upper circle and lower circle. These are the two edges of the cylinder. And then periodic boundary condition in the direction of this direction. And the typical Hamiltonian has this form. It's like the one we've seen before. So it's a second quantization of a single particle Hamiltonian plus a many body or density-density type interaction. With respect to before, I'm also including internal degrees of freedom. That's just to make the setting more general. But I mean, there is no big conceptual difference to what we had before. So this Hamiltonian H and V, they're both short-ranged. I will not specify their explicit form, but I will assume that they're both translation invariant. So the full many-body Hamiltonian commutes with translations in the direction of the periodic boundary condition, so that I can also, for the single particles, I can introduce a notion of quasi-momentum on the circle. So the assumption is that the single particle Hamiltonian has a bulk spectral gap, and it supports edge modes at the Fermi level. So this is something that you can read off from this picture, right? So these blue dots would correspond to the bulk spectrum, and what I'm doing, I'm choosing the Fermi level to be in a region where the Fermi surface is actually given by points given by the crossing of these edge modes to the straight line defining the Fermi surface. Okay, so my only excitations at the Fermi level are given by the edge modes that may be there, and this is one case in which they appear. This plot is from the Hofstadter model for a certain value of the magnetic field. Okay, so this is the model. Of course, the equilibrium state is defined in the usual way, and I would like to study this in a statistical mechanics sense. Right, so now what about perturbation? So I want to drive current on the boundaries, and a natural way of doing that is by making, again, the Hamiltonian time dependent, and I will do that in this very specific way. So I'm introducing a small perturbation, extensive one, which is slowly varying in time and slowly varying in space. This n of x is just a density operator, and this mu of x is just a bump function at the point 0. Okay, so this is just a bump at 0. It's a potential, if you want, that couples to the density. And I'm stretching this bump by enlarging its support by scaling the argument by theta. Okay, so think of this big region here to be the support of this perturbation, and that's where my perturbation is at. So about the observable, I want to look at edge currents. And the way I'm defining this, it's starting from the current density. So this J1 is the current density associated with the direction of the edge. This current density, in fact, is the operator that fulfills the lattice continuity equation for the variation of the density. Okay, so it has an explicit expression, but let me just say that this is all we need to know is that J1, J2, the two current densities are the two local operators that satisfy this lattice conservation law. And so what I do here, fixing a point on the boundary x1, let's say x1 is 0, I'm defining this edge current by summing over all these current densities in this red window. Okay, so I want to sum over all the current densities for x2 between 0 and this L, where L will go to infinity at the end. Okay, so that is my observable, and then I'm interested in the response function, the response of the expectation of this observable because of the perturbation. Right, so it turns out that the linear response of this edge current at 0 can be rewritten in this way. This is not entirely trivial. It, in fact, it uses information about fast decay of correlations in the bulk, which is something we actually prove later. But let me just give you the formula here. So this is, again, the linear response with respect to mu. I find it useful to take the Fourier transform in this variable x1, and this 0 is just x2 equal to 0. So it's the perturbation projected on the edge. So this G is something that depends on all the microscopic details, and it's expressed in terms of a lattice correlation function. And it turns out that up to subleading terms in theta and eta, this is given by this expression that is in fact the Kubo formula. Okay, so what you have is a commutator of the observable with the time evolution of the perturbation, and then since we're in Fourier, we have this plane wave factor here. And then ultimately we are summing over all the points y in a big strip of width a. Okay, so this a actually has to be taken to infinity before little l. So, so this is the edge response function, and what I'm interested in is trying to study this object here as a function of eta and p to understand the linear response of these edge modes. So one point I would like to make here is that, in fact, the order in which you take the limit eta and p to 0, which is in fact the limit of that gives you at the end a static perturbation and a perturbation that is almost constant in space, this order matters. If you first take the limit as theta goes to 0, then basically it's as if you are looking at the response to a constant perturbation, so number operator. And of course, the number operator commutes with everything. So in particular, this commutator would be 0. Okay, so this response would be trivial if you would take to 0 p before eta. Okay, so the natural limit to look at is to first make the perturbation static by taking eta to 0 and then making it very slowly varying in space by sending p to 0. Okay, so this is going to be my limiting edge transport coefficient. Now, before telling you what we can say about it, let me tell you a few things about an effective description for edge currents, which plays an important role in our analysis, which is the Lattice liquid. So I would like to introduce that in a quantum field theory language, and I will do that in a formal way, but of course it can be made precise. But at this stage, I just would like to be a bit formal and introduce it as this QFT as a formal Grassmann integral over a field psi. Okay, so this psi is a Grassmann field, which is a Euclidean field. It's labeled by space and time, x0 and x1. And omega is the chirality label of this field. Okay, so it's related to the chirality of the edge modes, if you want. So this is the action of this QFT. The first part is the non-interacting part, and it's relativistic field theory, as you can see. So this V of omega is the velocity of the fermions, and here there is some field strength that I'm also introducing. The second part is a density-density type interaction that describes the scattering between the fermions with a different chirality. And this is a short-range interaction. The important, I mean, there is an important underlying assumption here behind this choice of interaction, which only involves two chiralities of the time. This assumption is a elastic scattering assumption for the Fermi momenta. So you see, I mean, here we might have an arbitrary number of chiralities. These chiralities correspond to the edge modes. And this operator here is a 4-fermion operator. So in principle, you could have 4 different chiralities. The reason we have only 2 is that we are actually assuming that the conservation of the Fermi momenta at the Fermi level can only be realized in a trivial way. So either if omega 1 is equal to omega 2 and omega 3 is equal to omega 4, and then you have 0 equal to 0, or omega 1 equal to omega 3 and omega 2 equal to omega 4. Okay, so only 2 chiralities of the time are involved in scattering. And the reason why this is meaningful is that this is generically true. I mean, this Fermi momenta are continuous function of the chemical potential. So it could be that maybe accidentally this is true for some value of mu, but then if you change it a little bit, it needs not to be true anymore. So that's a generalization of the Lattinger model, which is in fact an important model in condensed matter physics that was exactly solved. It was solved by Mattis and Lieb in the mid-60s via the, in fact, first application of bosonization to condensed matter. Okay, so what can you do with it? I mean, an important thing, an important feature of this model is that it has an extra symmetry with respect to the lattice model, and that's apparent symmetry with respect to local chiral gauge transformation.
Can I ask a question?
Yes.
How do you define the functional measure capital D psi in the previous page?
Yes. Right. So this is formal at the moment. In fact, I'm going to comment on that in a moment. So this has to be defined properly. One way of doing that is by introducing a momentum cutoff and making everything finite dimensional, and then you remove the cutoff. Okay, but at this stage, everything is formal. Okay, so formally, what seems to be true is that if you perform this phase transformation, which in fact is a Jacobian equal to 1, this transformation actually seems to imply that the generating function of correlation function, so the partition function with an external field coupled to the density, satisfies this identity, so that somehow physics doesn't change if you change the vector potential if you shift it by a gradient. Okay, so this is a formal implication of this this identity. In fact, it's a false implication, but why would this be paradoxical? Well, the reason is that if you would now start from this identity and take derivatives with respect to the external field and with respect to alpha, you would get strange identities for the correlation functions. Okay, so if you take one derivative with respect to A, one derivative with respect to alpha, you would, on the right-hand side, you would get the density correlation function. On the left-hand side, you would get 0. So you would get something very strange. So instead, the point is that everything has to be defined introducing regularizations, let's say a momentum cutoff. And the consequence of that is that this implication is no longer true. And what you actually have is that the density correlation, so somehow this implication is no longer true. There is another implication, a more involved one that follows from this symmetry. And the consequence of that is that you actually no longer have that the density correlation function is 0, but it's a rather involved function of the momenta is 0. Okay, so this is much more involved than this. Of course, it depends on all the parameters that appear in the action, which of course at this stage are free parameters, and in fact it also displays a singularity at 0 momentum. So the limiting value depends on how you take the limit. It also mixes the chiralities because of this matrix T, which is the identity only if lambda is 0. Otherwise, this is not the identity.
And isn't it related to the instantons and like the index theorem?
I don't know. Maybe, but I cannot really say much about it. I'm sorry. So these are anomalies, in fact. So this right-hand side here can be understood as an anomaly. So probably as an index theorem. So this is one relation for the density correlation function. Similar relations can be found for other correlations like the vertex function, like this type. And this type of identities actually encode the solvability of this model from a QFT point of view. Okay, so this is very nice because, I mean, if you're able to extract the scaling limit from the edge physics, then you can try to use these identities to have a good understanding of the scaling limit of correlations. And that's what we do. So let me now present the theorem that's about now a two-dimensional lattice model of the type I presented before. So H is the many-body Hamiltonian. H naught is second quantization of a single particle Hamiltonian displaying edge modes. This is a short-ranged weak many-body interaction. I'm assuming translation invariance in the direction of the edge, and I'm assuming the presence of arbitrarily many edge modes, satisfying this assumption star, which was this assumption about having only two fermions participating to the two-body scatter.
Oh, I just heard that you said second quantization, so you're setting the underlying Hilbert space to be the Fock space?
Yes, exactly. So
then what about the wave function renormalization that is caused by the interaction?
So this has to be okay. So now I'm back to the lattice, and later this wave function renormalization in the field theory. If you want to use that field theory to describe properly the lattice model, you have to choose them properly. But they're fine. They diverge with an anomalous exponent, in fact, in the infrared.
Okay.
Yeah. So this is a theorem with Vieri Mastropietro, and it gives you an expression for the edge response function. So this is the edge response function for small eta and small p. And it's given by this formula here, up to errors which are either exponentially small in L or things that vanish continuously in eta and p. So that's what this little of one means. So in this formula, there are several symbols. I mean, this V is interaction-dependent velocity of the edge modes. It's something that is given by a convergent series in lambda. And this R is an explicit function that I'm not writing because the explicit form doesn't really say much, but what I want to tell you is that this is perturbatively close to 1, and in fact it is exactly 1 if you take eta to 0, which is the limit that we're interested in. So in particular, if you take the limit in the order I gave you before, if you take eta to 0, then p to 0, and then L to infinity, you see that something very nice happens, because if eta goes to 0, this goes to 1, this disappears, and this is also 1, and then you're left with the sum of the chiralities of the edge modes. So you recover the right-hand side of the BuEdge duality in terms of a limiting response function. So this is the result. Now, let me make a few comments about it. The proof is based on a renormalization group, which I won't discuss, but just a few words about it. So one, I mean, the way in which this is done, it's in a multi-scale analytic fashion. There is a first step in which one integrates out the bulk degrees of freedom associated to the somehow massive modes, if you want. And by doing that, the problem is reduced to an effective one-dimensional model that describes the edge currents. Very complicated one, but a priori explicit one. So this one-dimensional model is now gapless because of the edge modes, and it turns out that the quartic coupling of this 1D model is marginal in the renormalization group sense. So you have to study the infrared flow of this marginal coupling, which in general is a difficult task. But what we crucially use here is the integrability of the Lattinger model. So the integrability of the Lattinger model, from the renormalization group point of view, it tells you that somehow that this dynamical system converges to a limit thanks to the vanishing of the beta function. So this is, of course, an important concept in the renormalization group terminology, which play a very crucial role for our analysis. So all of this allows
Marcello, sorry, there is a question in chat.
Yes, I don't see the chat, sorry.
Yeah, that's the order of the limits on slide 16 matter. So the
yes, if I first take p to 0 and then eta to 0, I get 0. But yeah, you can see it here. In fact, if you take p to 0, if you keep eta fixed and send p to 0, this goes to 0. So this is, in a sense, if p goes to 0 for fixed eta, it's like perturbing with respect to the number operator, and then you get a trivial response.
Yanis, is this okay?
But it's not mathematically forbidden to interchange them. That's what I was hinting at.
You can do it, but you get a different result.
Okay. Thank you.
Yeah. Okay. So, right. So the RG analysis gives you good quantitative understanding on scaling limit of correlations, but then universality arises from conservation laws, and that's in fact the last part of my presentation. So the method is robust enough to compute, in fact, other transport coefficients like Drude weight and susceptibility, and this is something that we did in more restrictive settings in the past, and in fact, nice results can be proved. And however, I prefer not to comment on that. I can do it, of course, if somebody asks, but I will leave these remarks for this one. Okay, now let me give you a few elements of the proof. So the starting point is the rewriting of this edge response function after Wick rotation. So this is now something that is written as the Fourier transform of a Euclidean correlation function. And this Euclidean correlation function is what you can study using renormalization group methods. In particular, you would like to extract from this object its contribution due to, somehow its approximation via the Lattinger model. Okay, so heuristically, what you expect is that for large times, so for large Euclidean times S and for large Y1, so if you look at very far from the point where you want to make a measurement, the scaling of this edge correlation function should be ruled by the analogous object for the Lattinger model multiplied by the amplitude of the edge modes that gives you this exponential damping in the bulk. Okay, so this is the kind of thing you would expect at large distances. The Lattinger liquid arises as the model that gives you up to multiplication by the edge modes, the correct decay on the boundary. So this would indeed allow you to obtain this splitting in which the response function is given by sort of the Lattinger contribution plus a regular part, and to determine the scaling part because we have good identities for this correlation function for the Lattinger model. So that is nice, but it's not quite correct. And the reason is that the scaling limit contribution is also affected by the integration of this bulk degrees of freedom. So this Lattinger liquid approximation has to be weighted by suitable free factor that depends on the integration of the massive modes. So more precisely, the thing one can prove is this type of decomposition. So this is the edge response function, and it's given by a sum of two terms. There's the first term that it involves the correlation function of the Lattinger model up to some weights. And this should be an omega prime, sorry for that. And the second term is a regular part that somehow is more regular in momentum space, or it decays faster in configuration space. Okay, so this D is a matrix whose entries are the density-density correlation function of the Lattinger liquid. And this Z0, Z0 and Z1, these are a renormalization of the density and the current insertion due to the integration of the bulk degrees of freedom. So this is what you have. This is quite explicit because of the formulas we have for these correlators. This part is not explicit at all, but it has improved. This object is discontinuous at 0, while this one instead turns out to be continuous at eta and p equal to 0. Okay, so that's all you know. So how do you proceed from here? Well, you use a very simple observation, which until now it looked like a trivial observation, but it's in fact a very useful one. So the fact that the perturbation to constant perturbation is 0, this seems like a trivial fact, it gives you a non-trivial information on this part here, right? Because this 0 is the sum of these two terms. And this term here is explicit. So you know that this regular part at p equal to 0 is equal to minus this one at p equal to 0, which is remarkable because the left-hand side is something on which you have no explicit control. On the right-hand side, this is something that is defined starting from a relativistic theory. Okay? So that's one information. However, unfortunately, that's not the order of limit we want to consider because we're taking p to 0 before eta. But then what you use here is that you know that this guy is continuous in eta and p. So the limit as eta goes to 0 of this guy is in fact equal to the limit as eta goes to 0 and then p equal to 0. You can interchange the two limits for this regular part because you know that it's more regular than the first one. Okay? So this is the observation that allows you to determine this highly non-explicit term starting from something much more explicit, starting from a conservation law. And then what do you do with that? Well, you bring in this observation in the limiting value for this response function, and what you get at the end is that the limiting edge response function is completely determined by the effective field theory, by the Lattinger liquid, but in a very subtle way. So if you use this the fact that this guy is equal to the limit of this guy and you put it here, you find out that the limiting value of the edge response function is related to the discontinuity of this matrix at 0. Okay, if this was continuous, then it would be 0. So this means there would be no edge modes and the response would be trivial. But because of the fact that you have edge modes and you have this emergent Lattinger liquid description, this guy is not 0, and this will give you in general non-trivial transfer. So that's very nice, but still not sufficient to prove universality because you're still left with these parameters Z0 and Z1, which at this stage we don't know really what they are. They're given by complicated convergent series, but we cannot compute them explicitly, and we actually want to prove that this is an integer. Okay, so that's still far. So what we do here, and that's how I will conclude, is to again use conservation laws. And I will cheat a little bit here. I will actually, in the following, I will neglect the x2 label. That's the coordinate in the non-translation invariant direction. The reason why I'm doing that is that these coordinates ultimately are always summed in what I'm doing, and they don't really play a role. So from now on, I will pretend that my model is one-dimensional just for the sake of explaining you how things proceed. So what I want to use is again a conservation law. I want to use the lattice continuity equation for the evolution of the density in terms of the current density. And then what you can do here is to find out that this nice conservation law has a consequence at the level of correlation function. That's an example of word identity. It's very simple. You just rewrite this correlation function in configuration space and differentiate with respect to time and use the conservation law to obtain this non-trivial right-hand side. So the reason why you have a non-trivial right-hand side is because of this time ordering operation, which introduces a discontinuity in time. So this looks very much like the vertex word identity that you have in QED, let's say. That's very important there. And here we're using it at the level of this lattice model. So all these hats denote the Fourier transform in space and in imaginary time. Okay, so this is an exact identity that you have for the lattice model, just following from the lattice continuity equation. There is another identity of this type, which is obtained from the Lattinger liquid, and that follows from its integrability, in fact, or if you want, it follows from the fact that you can compute all correlation functions via word identities. Okay, so this is a consequence, again, of this, I mean, it's what is called the anomalous word identity for this Lattinger QFT, which relates this vertex function, so this is a density operator and these are the two fields, in terms of the difference of the two-point function as in this case. So it looks, of course, it's a different model and it's a different, the objects are different, but the structure is similar. On the left-hand side, you have a vertex function. On the right-hand side, you have difference of two-point functions. So then, of course, there is a mixing of the different chiralities because of this matrix. That's because the interaction mixes the chiralities, but the structure is very similar to what. So these are two identities that don't talk to each other, and to let them talk, you remember that, in fact, the Lattice liquid gives you a description of the scaling limit of the model. So in momentum space, that means that the singularity at small momentum of this correlation function is described by the Lattice liquid. Okay, so to do that, I mean, to have that this is true at a quantitative level, you have to choose properly the bare parameters in the action of the Lattice liquid QFT to have this quantitative agreement between vertex functions. So the Z0, Z mu for mu equal to 0, 1, these are precisely the parameters that entered here, and they are in fact due to the integration of the bulk decrease of freedom. Okay, so this is now the way in which these two models talk to each other. You tune the parameter of the Lattice liquid to have that the correlation function have the same singularities. And then once you have that, you actually realize that the two equations are actually two equations for the same objects, right? So the second one is an equation for purely for the Lattice liquid QFT. The first one is an equation for the lattice model, but if you plug in this asymptotic result in the first equation, you end up with two equations for the same correlators, which are the correlator of the lattice liquid cube. Okay, so you have two equations which have to hold for the same objects, and the only way in which this equation can hold is by having non-trivial relation between all these complicated parameters that we catched up along the way. Okay, so you cannot compute these parameters explicitly. They are given by convergence series, but the fact that these two equations have to hold at the same time gives you a constraint between these two parameters, which is unavoidable. And the miracle is that this constraint is enough to prove a cancellation in this object and to prove universality at the end. Okay, so this is how how this universal result for the edge response function is found. And in fact, the same ideas can be used to actually compute the response function for non-zero eta and for non-zero. Okay, sorry, let me just conclude. So, right, so I presented so I'll give you an overview of an approach to study transport for many body systems with a focus on, in fact, real-time response coefficient for gapless models. And this method, in fact, it can be used to prove universality as a result of a combination of certain ingredients. So the first one is to isolate the scaling limit, use the special integrability properties of the scaling limit. In our case, we had them because of the Lattice liquid, and then use this general information you have from conservation laws to constrain all the parameters that you accumulate along the way and to actually show cancellation. Okay, so this is how it worked for the case study I presented now. And then, of course, there are many open problems that are left to be studied. I mean, here I started from the linear response ansatz, and as I said, that this ansatz can be proved to be rigorously correct. So to prove that the errors are really small in epsilon and uniform in the volume for gap system. So the question would be to actually prove the validity of linear response for gapless systems, and this is something on which I'm working on with my group here in Trieste. Another interesting question is to include disorder. So in all the story I told you, it was very important to have a translation invariance in the direction of the edge. I mean, from what I told you, it's not so clear how, because in fact it's because the renormalization group analysis works if you have this translation invariance. But it would be very interesting to break this translation invariance with disorder, not just to create an extra technical problem, but because there are interesting questions about universality or non-universality of suitable transport coefficients for quantum Hall systems, which depend or not on the presence of disorder. And that's, in fact, the context of this series of works by Kane, Fisher, and Polchinski at the beginning of the 90s. Okay, so that's all I wanted to tell you, and I thank you very much for your attention.
Thank you very much, Marcello, for this very clear talk. We have some time for questions. If anyone has any questions, feel free to either unmute yourself or raise your hand or write your question in the chat.
Can I ask a question? So you had this result, final result for conductance G, and you said it's universal. So, but of course it's a beautiful formula, but it's sort of complicated. And what do you mean by universal? That
so I mean the universal object. You're right that the universal object is the limiting value.
Okay.
So the limiting value, this is universal because it's the sum of the chiralities of the edge modes, and these are, they don't, I mean, this V of lambda is, you know, it's given by a convergent series around the non-interacting velocities. So these signs, they don't change. They're the same signs of the non-interacting case.
Okay, so
this is the same.
So when
Sorry.
okay, before taking the limit, this G is not universal, and you still have.
That's right. Yes. Yes. So I mean, of course, I mean, this quantization is no coincidence. I mean, it could be that there is somehow a more general topological argument that gives you that. But in my view, what I like about this is that, in fact, the method gives you good control also on the non-universal thing. So in fact, on all the dependence of this response function for general value of beta. And then in certain limits, you get something which is quantized, but if you don't take the limit, you get a function, which is interesting.
Okay, thank you.
I have a question.
Yes.
First, so you assume that the whole theory is asymptotically free in that if the lambda goes to 0, then the theory converges to the free theory?
No, I don't assume that. So what I prove is that in the deep infrared, the behavior of the theory is in fact very similar to the one of the Lattinger model, which is not an asymptotically free theory. So the Lattinger model, the quartic coupling flows to what is called a line of fixed points, and the infrared, you know, the fixed point of the flow of the running coupling that describing the scattering of the fermions converges to something which is not 0. So this is the vanishing of the beta function for the Lattinger model. So it's a truly interacting theory, the Lattinger model.
Then is it possible to obtain the continuum version of this lattice theory?
Well, I mean, the Lattinger model is the continuum version when you look, you know, I mean, you look at things from far away and then you rescale, and that the continuum version of the model is the Lattinger model up to this tuning of the Baire parameters. So if the question is to send at the lattice level the lattice spacing to 0, that's another question, and that's sorry?
Yes. My question is whether or not the limit exists if you send the lattice spacing to 0.
So that's a very hard problem, and I don't know. In fact, I never thought about it. But there you're introducing a serious ultraviolet problem because of the lattice spacing going to 0. I mean, it should be I mean, somehow.
As you said, the theory is not asymptotically free, so even if the limit exists, it may not coincide with what you just said, the theory, the continuum version of the theory.
No, but the way in which I'm talking about continuum theory is not by sending the lattice spacing to 0, is by looking at large distances and then rescale lengths, right? So I mean, I'm not taking the lattice spacing to 0.
I see.
Okay, so it's you look at the system at you know, large distances, and then once you rescale space variable, you can approximate a correlation by a continuum theory or small momentum if you want, and that's what the Lattinger limit does for you. But I'm not taking the lattice spacing to 0.
Are there any further questions?
Can I ask one more question? I think this is a frequently asked question. So your approach is based on the philosophy which is different from the topological point of view, right? So is this philosophy based on this conservation and so on? Is it complementary to the topological point of view, or I mean, is it a different way of viewing the same?
So that's a very good question.
I could ask. For example, I could ask if there is a problem that which can be attacked by this method, but not by topology, or vice versa.
So, I mean, the method, as I said before, it gives you access on a priori, not just this transfer coefficient, but also other ones that are not topologically protected. So an example I was giving before is the Drude weight and the susceptibility. So, so Drude weight is related to current correlation function. Susceptibility is density correlation function. These two objects in general, they're not universal. So they, even at 0 momentum, they are interaction dependent. and there is nothing, there's no topological argument that tells you what their values is. What the values are. But what you can prove, I mean, you can access that with the method I'm using. And in fact, one thing you can prove is a consequence of, it's something that is usually obtained via bosonization from a formal point of view, which is this so-called Haldane relation. So the ratio of the Drude weight and the susceptibility is equal to the Fermi velocity squared. So this was an identity that was discovered by Haldane by looking at one-dimensional systems, again using bosonization. And the nice thing is that this can actually be proved at the level of edge currents. In fact, it has been proved also rigorously for one-dimensional system by Benfatto, Falco, Mastropietro, but here we did it also for edge modes. And so this is an edge Drude weight and an edge susceptibility. And the thing is that nothing in this identity is universal. So D is interaction dependent, K is interaction dependent, V is interaction dependent, but they satisfy this nice relation.
Okay,
So this is an example of something you can compute. And then, I mean, of course, more generally, you know, you have this type of expressions where, you know, you have no universality, but you have good analytic control. Of course, the limitation is that it's all based on ultimately on convergent expansions, right? I mean, a multi-scale expansion, and lambda has to be small. Okay, so that's what the method needs. Yes.
Yeah. Thank you.
In what exact sense do you mean by topology? Because if you're working on a lattice, then everything is just discrete, and the topology is discrete on the underlying space. That's what I understand.
Sorry, I didn't understand the first part of the question.
In what exact sense do you mean by topology? Because the lattice has only two topologies, the discrete or indiscrete topology.
No, but it's the usual sense of the quantum Hall effect. I mean, even if you just take non-interacting fermions on a two-dimensional lattice, you can write the whole conductivity as a Chern number of a suitable bundle on momentum space. So the topology is a topology that you observe in momentum space in the case of translation invariant system. So that's a general story about the quantum Hall effect, right? The whole conductivity can be written in translation invariant setting as a Chern number of a bundle which has at the base space the torus of the Brillouin zone, and then the fibers are you know, the range of the Fermi projector at a given point on K.
Oh, I see. But by the Chern number, that's what I meant by the index theorem. I see.
Yeah. So that's okay. So for the whole effect, that's how it comes in. Yes.
Okay. Well, thank you very much, Marcello, for this very clear lecture and for answering all the questions. We will be back in 2 weeks with a talk by David Hughes, who's going to talk about many-body localization, and I hope to see everyone there.
Thank you very much. It was a pleasure. Thank you.